To understand the background and implications of best linear unbiased estimation, let's go a bit deeper into its origins. Here you see the final appearance of the best linear unbiased estimator x hat. It is clear that apart from the observables in vector y, it is dependent on two components, the design matrix A and the covariance matrix Qy, or actually the inverse of the covariance matrix. The other estimators, y hat and e hat, remain unchanged from the way we introduced them earlier. In this video, let's look a bit deeper into the elements of BLUE. BLUE is an acronym for Best Linear Unbiased Estimation. We already know what estimation means. We want to find a value for a parameter which is as close as possible to its true but unknown value. Also, the concept of linear estimation has been introduced. If we consider the general form of our functional model and consider the weighted least squares estimator x hat, we can see that it is indeed a linear function of the observable vector y, which is easier to see if we lump all matrix multiplications together. Similarly, it follows that not only x hat, but also y hat and e hat are linear estimators. The third element in the acronym BLUE represents unbiasedness as a property, which we also have seen before. Recall that when an estimator is unbiased, this means that we expect the value of the estimator to be equal to the true but unknown value of that parameter. Given our linear model of observation equations and the weighted least squares estimator x hat, it follows that indeed the expectation of x hat is equal to the true but unknown value of x. Now, the first letter of the acronym BLUE, the B, is actually the most important one. It tells us that the estimator should be best, and the term best always needs to be defined explicitly. In the context of estimation theory, best means that out of all possible estimators that one could imagine, we want to select the one for which the precision of the estimator has the lowest value. Let's spend a minute to grasp this. In this generic expression of the weighted least squares estimator x hat, there's only one element that we can influence to change the value of x hat. That is the weight matrix. Therefore, if we introduce 1 million different weight matrices, we will get 1 million different outcomes for x hat. Now, the term best implies that out of those million outcomes, we would like to find the one that has the best precision. If x would be a scalar, the best precision corresponds to the lowest variance of x hat, or the lowest standard deviation. Let's work this out in some more detail. This is again the generic weighted least squares estimator of x hat, of x. If this is the case, then we are interested in the covariance matrix of x hat. If we apply the covariance propagation law, and if we fill in all the terms, we get a long expression. Note the symmetry of the expression. As you probably will have seen in the exercises, it follows that this equation can collapse to a much more elegant form. For this to happen, we should replace the weight matrix W with the inverse of the covariance matrix Qy. Let's clean up what we have obtained now. The center part of this equation can be cleaned up further by removing the product of the covariance matrix with its inverse. This yields a product of 3 identical square matrices, of which 2 are inverted. We can therefore eliminate another product of a matrix with its inverse, and we can find a short and elegant expression for x hat. Let's look at what we've got now. We see that if we would use a specific weight matrix, the inverse of the covariance matrix of the observations, then the covariance matrix of x hat has an elegant expression. Moreover, this expression is now only dependent on 2 things, the A matrix and the covariance matrix of the observations. Intuitively, it makes sense that we use our knowledge on the quality of the observations to compute the estimator of the parameters. It can be proven that this expression for the covariance matrix of the parameters is best. Of all possible weight matrices, this particular one gives us the optimal estimator of x hat. In other words, this x hat has the highest precision possible. To finish this video, I would like to return to the easy sea level rise example and recap what the equations will look like if we use blue as our estimation procedure. We formulate our y is ax problem using the expectation operator and the corresponding stochastic model expressing the dispersion of the observations by its covariance matrix. We then find the best estimate x hat. The quality of the observations is captured in the covariance matrix of y, and it is indicated conceptually in the figure by the red bars. The length of these so-called error bars depends on the standard deviation of the corresponding observable. Essentially, we minimize the differences between our actual measurements, which are the red dots, and the linear model which we assume to be applicable, which is the green dashed line. We do this by giving some observations more weight than others, which follows from the inverse of the covariance matrix. In the plot, the observations with a bigger error bar represent observations with less precision. The differences, or residuals, are indicated by the little vertical blue lines, and we call these the least squares estimates of the residuals, or E hat. Mathematically, we obtain this solution by minimizing the weighted sum of squared residuals, which then yields the best linear unbiased estimate. In this video, we have elaborated on the meaning of the three components of blue: the linearity, the L, the unbiasedness, the U, and the best, the B, properties of the estimator. We also saw that blue is a particular case of a weighted least squares estimator. Although blue is the best of all weighted least squares estimators, it is also more demanding. In order to obtain the blue estimator, we need to have complete a priori knowledge about the covariance matrix of the observables.